All right, let me get another solution here. How about chapter 30, number 45? And I thought I better do this one too. A few people are asking questions and kind of stressing about this one, and rightfully so. Let me begin the same way I did with 39 and 43, that this one here is about the magnetism of matter. This is more of an extension towards your second class on magnetism, the class you will take when you transfer to whatever school you transfer. I'll just say you leave here and go to UCSB. So you transfer here and go to UCSB, and you take that next level class on electricity and magnetism. You will probably review a little bit about the magnetism of free space that we're learning now, but then you'll quickly jump into the magnetism of matter and what happens if you have things like iron or cobalt or nickel or potassium or aluminum or magnesium floating around. And so those are some really interesting questions. And I wish we had time to deal with them. But since they are kind of the next level, and the Survey book in section 7 even does a little bit of asterisks on it. No, I'm sorry, that's the OpenStax. The OpenStax section 7 puts a little asterisk. The Survey, it's in section 6, but he doesn't really put an asterisk. But I probably should. Just kind of an indicator to you to say, look, this is kind of on the next level. So it's good to see it. And that's why I assigned this homework problem along with 483 and along with 65 and 66. They kind of get your feet wet, if you will, about the magnetism of matter. But I want to say again that it will not be on the exam. We're not going to have anything on the exam of the magnetism of matter. I just, put it in part of the reading. I put it here as a couple homework problems. I'm not even sure on the lecture videos if I got a chance to say even much about the magnetism of matter. I should probably go back and look at that. So I think that's what was going to make it kind of hard for you to do. And so again, I just wanted to start this video saying, don't stress about it intense, that it's not on the exam, but at least go through this solution and at least look at it, because what I hope you get out of that section is that, if you have a piece of iron, and so let me just take this iron bar here or something, and you make it into a magnet. So this is a North Pole, this is a South Pole, and the magnetic field is arcing around. Where does that magnetism come from? And we hopefully have learned that all magnetism comes from moving charges. So if this piece of iron is not plugged into a battery, where are the moving charges? And that would be then that the electron both orbits, so it revolves, and it spins as it goes around. And it turns out for iron that there's 26 electrons, and half of them go clockwise and half of them go counterclockwise. So there is no net current and net motion for their orbiting. They also spin, and it turns out that, let's see, out of the 26, 24 cut in half is 12. So 12 of them are spinning up, and another 12 spin down, and 2 more each spin up. So I guess that makes 14 up and 12 down. So the 12 and 12 cancel each other off, and you're left with just 2 spinning in the same direction, and so that is a net effect. And so your magnetism in a piece of iron comes from the spinning electrons. That conceptual idea is probably as much as you really need to understand for the magnetism of matter. Because that's where then, then how many electrons do we have spinning in that way? And so as I just said, for iron, there's 2 of them. In fact, that was our calculation in number 43. So if you haven't looked at the solution of 43, you might want to go through that solution, was to calculate that if we made as strong as magnet as we possibly could with iron, we would get 2 of them. And so that's why I'm talking about 2 of them, because that's the best we can do, given the other restrictions of quantum mechanics and the Pauli exclusion principle. And for any of you who know chemistry, you know what I'm talking about in those d orbitals. Okay. So understanding the material itself, you got to know a little chemistry. You have to have gone through this class. And so, like I said, this is kind of the stepping stone to the next class. And so I want you to see it, but I don't want you to stress about it. It's definitely not going to be a problem like this on the exam. And in fact, problem number 65 and 66 are taking a little ball of charge and spinning it and then actually calculating the magnetic moment from a spinning ball. And so that's why I would put 65 and 66 together in this chapter on the magnetism of material. However, that being said, making the magnetic moment of spinning charges, you can just treat that as a current. So 65 and 66 you shouldn't have troubles with. They're just moving charges, and so that one you should know how to do. Although the problem is a hard problem, so I don't mean to say it will be easy, but it doesn't have to really do with the material of matter. But it is trying to show you how a charged ball, like an electron, if an electron is a charged ball and it spins, it would make a magnetic moment. And so that's what's neat about 65 and 66. But back to this problem, number 45. This is saying that they're gonna line up. All right, so let me read number 45 here. It says that the magnetic moment of the Earth. And so we know the Earth is magnetic, and it has a big iron core. But it says that the magnetic moment, and so mu, of the Earth is approximately 8.0 times 10 to the 22, and the units for a magnetic moment, if you remember when we did we did magnetic moments with a current on a loop, and our torque of our motor would be, the units of an amp and an area. In fact, we did it this way. We said the magnetic moment would be the current and then the area, okay? And that's what you would get if you just had a current in a loop going around. Here we have a bunch of electrons going around, or actually they're not even going around orbiting, they're spinning. But that's the magnetic moment. So that's what they're saying here. And so in A it says, imagine that the planetary magnetic field were caused by the complete magnetization of a huge iron deposit. How many unpaired electrons would there be? Okay, so in that section, they point out by an experimental measurement, which, by the way, that's why problem number 65 and 66 are kind of cool. You can actually calculate the magnetic moment from a spinning charged ball. But they just say that the magnetic moment and is let's see, I should have this memorized, 9.27 times 10 to the negative 24. And so that's how much of a magnetic moment you get from one spinning electron. So what we must have is a bunch of them in order to get this. Let me call it n of them. So this problem is a pretty simple calculational problem. It's not meant to be a hard calculational problem. It's just meant to see, do you understand the idea of magnetism coming from these electrons? So if we just grab the calculator now and divide these two, 8 times 10 to the 22 divided by 9.27 times 10 to the negative 24, I get a number of 8.63 times 10 to the 45, okay? And so this is how many electrons must be unpaired, that is spinning in the same direction. Because again, if they're paired, they cancel each other off. And so I'll go back to the iron that's got 26 electrons. There is, say, 12 of them spinning upward. Usually we put an arrow up. And then another 14 of them, say, spinning the other direction, spinning down. And so matching an up with a down would cancel off, and the net effect is 2 are spinning down. Or just 1, kind of depends on how the iron is arranged. And it could be some with 2 and some with 1, so there's an average of about 1.5 or something. But anyways, we have this many. And now, obviously, they're not all from one atom. The atom only has 26 electrons, but there is clearly a lot of atoms, and each one contributes probably about 1 to 1.5, maybe 2. 2 would be its maximum it could do, and then you would get this many. And so that's the idea of this problem, really. So again, that's I think A. I think there was a part B. Let me look here. So this is part A. How many do we have here? Yeah, see, because then B goes on. B says now at 2 unpaired electrons per atom. Okay, how many kilograms of iron would compose of this deposit? And then they give us some useful information here. Iron has a density of 7,900 kilograms per cubic meter, and there is approximately 8.5 times 10 to the 8th iron atoms in 1 cubic meter. Okay, well, let me start here by saying, well, let's just figure out how many atoms we're going to have. Because we just figured out how many unpaired we have, and now they're telling us there are 2, and like I said, that's the ideal situation. And so if everything was perfect for these iron atoms, we would have 2 contributing there. So if you take the 8.63 and you divide it by 2, what do we get? 4.3. Yeah, 1.5 times 10 to the 45. So that's how many atoms we would have, which obviously is a lot of atoms, definitely. Okay, so let me just write that number down here: 4.315 times 10 to the 45. So that's how many atoms I have. But they also told me that there was 8.50 times 10 to the 28th atoms. So maybe I'll put atoms per cubic meter. So this would tell me how many cubic meters I have. And so grabbing my calculator here, let me divide that first by 2, so I get that numerator. Okay, now let me divide that by, what do I have here? 8.50 times 10 to the 28th. And so I get 5.08 times 10 to the 16 cubic meters. Okay. And now if we use the density, so let me go times, there are 7,900 kilograms in every cubic meter. I'll get then the answer that they want, and that is how many kilograms would this be? So 7,900 comes up to an answer of 4.01 times 10 to the 20th kilograms. And so that's how many kilograms must be kind of in the center of the earth, and I should say that's if it's fully saturated, so there could be more kilograms here, but that's how many kilograms then we kind of suspect are contributing to the magnetic field. By the way, we do suspect that there are more kilograms or more atoms than this, because we suspect that some of them are there and they're in a liquid state here, so they're not contributing to the magnetic field. Or we're not sure. There's just a lot about the core of the Earth we're not sure about. Anyways, so there's the answer. But I'll say it again, the point of this problem really is to introduce you to this idea that the magnetism really comes from the moving charges. And in this case, in the case of iron, and many cases, it's not the orbital of it, it's the actual spin of it, and you get this much for every 1 electron. So when you have a lot of electrons, you get a huge magnetic moment from our planet Earth, and some planets have even a lot more than that. That's kind of small compared to some planets, but also it's pretty big compared to some planets. So a lot of them we're just not sure about. We can only really the ones we can send probes to, which are in our solar system. All right. Hope that helps.